That was wonderful. Thank you. I want to begin tonight by a little history. You folks were raised in one of the most exciting times in the history of mankind. I was born in 1945. The war was just over, and things were beginning to settle down. Science was blossoming. A lot of important things happened between 1950 and today in the world of science. Let me rehearse a few for you. Some of you will know about some of these, I hope. If you do, nod your head and make me feel better. It was 1953 that Watson and Crick discovered the structure of DNA, for which they won the Nobel Prize some years later. It was right around that same time, 52, that Stanley Miller and one of his students by the name of Harold Urey did some experiments based on the Oparin-Haldane hypothesis that I told you about last night, and I'm sure you remember every detail about that, on the origin of living things. Because they proposed that there was a different atmosphere in the early earth which allowed the origin of life, which doesn't allow life just to be originated these days. So Urey and Miller did an experiment in which they tested whether that might be possible, and they put some chemicals into a system. I don't have time to explain all that to you, but out came some of the amino acids. And over the course of time, several other things were produced in that kind of a system that seemed to be an unguided system. And of course, the argument was, here we've got non-living stuff producing the basic building blocks of living stuff. By itself, no God needed. About the same time, Frederick Sanger is given credit for being the first one to take a protein and tell how many amino acids were in it in an exact order. He won the Nobel Prize for that a few years later. Frederick was an amazing chemist, because some years later he won a second Nobel Prize. Nobody does that. For developing a method to sequence the DNA molecule in 1977. And about the same time that all of this was happening, there was a grand event, and I'll tell you the exact date, October the 4th, 1957. It involved outer space. Does anybody remember? Scared us all to death. Sputnik, thank you. By the way, this is a class. You can answer me. Sputnik, put up by the Russians. And of course, we all thought the Russians are going to take over space and rule the world. Scary time. And out of that came a huge movement in the United States funded by our federal government, which I was a recipient of because I received a full scholarship to Harvard under that program. Because I was a science educator and they wanted science teaching to get better. And that money was well spent. Pardon me. And I'm still a believer in God, like most of them aren't. But we produced a whole bunch of new curricula for high schools and colleges to make science teaching better. A lot of exciting things, ladies and gentlemen, in the 50s and 60s and 70s. As we began to uncover the secrets of the universe and of life at the biochemical level. Incredible time. A heady time for those who didn't believe in God. Because it was about then, April 8th, 1966, that this issue of Time magazine came out. Is God dead? And it was a subject on many people's hearts and minds, and on their pens as well. And so in this Times issue, several theologians, ladies and gentlemen, joined scientists in saying we don't need God anymore. He was a construct of human beings anyway. And it was at this same time that A.W. Dicus wrote the song that you just sang. And boy, did you sing that beautifully. Wish you could have been up here with it all just rolling over you. And what you said was, our God, He is alive. In Him we live and we survive. And the time that was written by A.W. Dicus, the former dean of the school where I sat in his seat for about 18 years, a highly respected physicist who wanted the world to know he wasn't going along with this mess. Our God is alive. And I thank God for him. He wrote several other songs you probably don't know. One of them was Lord, I Believe. You know that one. But there's about 30 others. I recently received a copy of the book of his songs from his granddaughter. And it's a treasure. But in that issue of Time magazine, Thomas J.J. Altizer and William Hamilton, theologians, ladies and gentlemen, preachers, said in their book, Radical Theology, The Death of God, we must realize that the death of God is an historical event, that God has died in our cosmos, in our history. The dead God is the God of the historic Christian church and beyond the church of Christendom at large. Imagine preachers declaring that God is dead. How in the world could you do that? You do it because you come to believe that man made him up in the first place, so we might as well kill him. This was common in the 60s and 70s and 80s when I was in college, studying science, sitting at the feet of highly intelligent professors, saying things like this: if you are a Christian in this class, you better get over it. It will be but a short time when we've uncovered the secrets of life, and the more we learn, the less we need the God you worship. That was very common, and certainly at Harvard University. It's interesting to me that here in 2021, there's a new book by Eric Metaxas called Is Atheism Dead? Don't you love it? That's the latest book I've read. It's not even in my bibliography because I just finished it. But you can see it up here and write it down. Is Atheism Dead by Eric Metaxas. Metaxas is a good writer. And it's a good book in a host of ways. And I want to read you a couple of the quotes out of that text. Since the Time article in 1966, of course he took his title from that, roughly 5 things have arisen to challenge, and I will argue to overturn, the secular consensus that formed in the wake of that article. Now, if you've not heard me teach before, you don't know that when I pause, I just said something important, and it will be on the test. I love what Metaxas said right there in his introduction. Because what was happening in that time when the Time article came out was there was a consensus developing that if you know anything about science and the natural world, you better get over belief in God. They don't go together. And he argues, this book, that in the last 70 years, the secular consensus that formed in the wake of that article, he believes has been overturned by science, and so do I. Which is why I'm so excited to talk to you tonight about the second lesson in this series. Here are his 5. The beginning. Did I talk about that last night? We now believe the universe, time and matter and space had a beginning. That is anathema to an atheist. Second, the fine-tuning of the universe. Did we talk about that last night? Not in the extent it deserved. And third, the stupefying complexity of living things. That's our topic tonight, in addition to what we did last night. And fourth, he says, archaeological discoveries that support the truth of the Bible. And fifth, he says, what atheism is and what it produces, we've seen better than ever in the history of mankind in the last 100 years. You just think back, class. Hitler and Stalin and Pol Pot and the whole USSR. Atheists to the core destroyed more human beings in the last century than in all the history of mankind put together. It is a horrendous thing what atheism has done to this world. Surely people can begin to see. I don't want to go there for all kinds of reasons. And so he argues very clearly, is atheism dead? Can a person be an intellectually fulfilled atheist anymore? I don't think so. The scriptures still teach that the study of nature should lead to belief in God. Let's read it again tonight. Romans chapter 1, verse 20, our theme passage for this series from the Bible. For since the creation of the world, his invisible attributes are clearly seen, being understood by the things that are made, even his eternal power and Godhead, so that they are without excuse. Not only does the Bible say you should come to believe in God by examining the things that are made, but you have no excuse for missing it. That's what this book says. And it says it very clearly in numerous places throughout. But I'm not speaking to you tonight from this book. I'm speaking to you tonight from God's other book, the book of the natural world, which also testifies grandly of his existence, as this book teaches. I hope if you're an atheist or an agnostic listening to this lesson, that you will be open-minded enough to listen to the evidences for the existence of God from the natural world. And were you to become convinced of that, I hope you'll get into this book and learn about Jesus Christ, his Son, and the plan of salvation. But my lesson tonight is about the science. So are you ready, class? We're going to talk tonight again about the argument from design. Because when something was designed, there had to be a designer. That's the argument. So I want to look at the evidence from the chemistry of living things. What better thing could there be for you to do on a Saturday night? Listening to me teach chemistry. You can be thankful you're here. If you hate chemistry, it's because you didn't have me. I'm sorry, but that's the truth. Thank you. I'm absolutely thrilled to explain to you some of the things, and again, I will make my apology like I did last night. When I get finished, I will have done a miserable, incomplete job of telling you what I ought to have told you, but I'm going to give you as much as I think I can stand and you can stand in an hour and a half. So here we go. We're going to talk about the chemistry of living things. And so why not turn to one of the foremost experts of our time, Mr. Francis Crick, Dr. Francis Crick, the co-discoverer of the structure of DNA. He wrote a book in the early 1980s called Life Itself, Its Origin and Nature. If anybody can tell you about the makeup of living things, it's Francis Crick. So I'm turning to page 72 of this little book. And let me read a few lines to you, and we'll use this chart up here to kind of summarize. Life as we know it on Earth appears as a synthesis of two macromolecular systems. And I just lost you. Synthesis means the makeup of, and macromolecular means big molecules. So in every living thing, class, every living thing we know anything about, there are two groups of giant molecules. Now, I'm going to do this several times, and you'll be very helpful to me as a teacher if you make some kind of reaction. Are you with me? Thank you. And nodding your head's okay, too. The proteins, so here you see before you, there are structural materials, which are proteins, that make up the shape and mobility of living things. The proteins, because of their versatility and chemical reactivity, do all the work. but are unable to reproduce themselves in any simple way. And so, there's another whole class. They're called the tools and machinery. They're called enzymes. But ladies and gentlemen, an enzyme is just a special form of a protein. So both of those first two groups are proteins. That is one great class of molecules that is in every living thing. Got it? Proteins. So say it. Good. We're going to use that a lot. The nucleic acids, you see there's another class of molecules called the blueprints. The genes, the nucleic acids, they're the DNA and the RNA. They make up the way to reproduce. The nucleic acids seem tailor-made for reproduction, but can achieve rather little else compared with the more elaborate and better equipped proteins. RNA and DNA. Good for reproduction, but not much else. So two. Now he goes on to say, the problem of the origin of life, because that's part of what he's about in this book, would it be a great deal easier to approach if there were only one family of macromolecules capable of doing both jobs, reproduction and the work. But life as we know it employs two families. That's a tough thing. And may I just take a little side trip here before we explain some of this in more detail? The DNA and the RNA have a big job to do, but they can't get it done without the proteins. The proteins do all the work, but they wouldn't even be here if the DNA wasn't here, because the code for the proteins in the DNA, so it takes DNA to have proteins, and it takes proteins to make the DNA do its job. Okay? That's the big picture. Now we want to put some little flesh on that bone as we talk more detail about this. All right, you're in my chemistry class. This is the first day of class, biochemistry. And we begin class, our discussion of proteins. And here's where you begin, because proteins are made up of these 20 common amino acids. Every protein in every living thing is made up of these. I don't care if you're a single-celled bacteria floating around in your intestines or if you're you. Every single one of you has proteins made of these things. So your first task, class, is to memorize these. By tomorrow, we will have a quiz on glycine, alanine, valine, leucine, isoleucine, proline, serine, etc., down to histidine. You will learn their names and their abbreviations. The following class, you will learn their structures. Now, I won't make you memorize every single structure. There'll be some key ones, but here's one thing you need to notice. Why are they called amino acids? Watch. Every one of them has an NH3 group. Can you see that as you look down here? NH3 is amine. A-M-I-N-E, amine. So they're called amino. Every one of them also has a COO group. That's an organic acid. So you see there's a COO on that one, there's one on that one on that one. Every one of them has a COO group. So they're amino acids, but every one of them is different. And we need all 20 of them to constitute the proteins that God has put in every living thing. Now I pause and take one other little break here for just a moment. Pay close attention, because I want to give evolutionists some due here. It is a fact, class, that every living thing has the same kind of chemistry. Why is that? An evolutionist would say that is because we can all trace our ancestry back in a tree of life to a single common source for all of us. We all have the same chemistry. We all came from the same source and evolved by natural causes. That's what they would say. That is not a stupid answer, class. That's one possibility. But there's another possibility. If there was a grand designer who wanted all living things to interact and interfeed and interbreed upon each other, why wouldn't he conform them to the same chemistry? mean, that's just as good an explanation or better, because it explains a lot of other things as well. But don't go out there thinking that everything an evolutionist says is stupid and not worth talking about. That's not right. All right, so the 20 amino acids are what make up all proteins. Every protein is some combination of these, much like the 26 letters of the alphabet make up our words in English. So if you spell the word disestablishment, I forget the word, but anyway, if you can spell it, you're going to use those letters, right? Okay. I'm skipping now to the other great class of molecules, the DNA and the RNA. We call them the nucleic acids. I'm getting over here with my glasses on, reading from Dr. Crick's book. So you know I didn't say this. I'm reading. RNA and DNA are the dumb blondes of the biomolecular world. Fit mainly for reproduction with a little help from proteins, but of little use for much of the really demanding work. I did not say that. But it's the truth. No. Apology to all blondes. But I've used this illustration a lot, and when I talk to people later, that's the thing they remember out of my lecture. It's okay. I won't take offense. But that's about right. They're good for reproduction, but if you don't have proteins, they ain't got nothing going on. And the DNA, as we've learned, has a helical structure. As you can see over here, it's strands that are wrapped around each other with cross pieces. So it's a double helix with crossbars. It has the capacity to reproduce itself, and it contains a language that has 4 letters in it. Now, folks, we ought to be spending the next 2 weeks on that. I'm just telling you, in DNA there is a language that we've learned how to read, and we know exactly what it's doing. And what it's doing is telling the molecules how to build proteins. For the most part. There's a lot of other stuff going on too, but that's what the language is for. And here is the language. You've surely all heard of the genetic code. And if this were my class, we'd spend the next several days teaching you how to read. Because in this language, there are only 3-letter words. So if you use 4 letters, taken 3 at a time, and you can have repeats, how many words can you make? I will tell you, it's 4 times 4 times 4. So do the math, class. 4 times 4 is 16 times 4 is 64. There are exactly 64 words in this language, and they're all up here. Because you see, you can take the 4 letters on one side, the 4 letters here, and the 4 letters here, and you can make all the combinations possible. And the interesting thing is, if you memorize what I told you to memorize a while ago, you can see that up here are all 20 amino acids. So the code TTT is phenylalanine. The code TCA is serine. The code CTT is leucine. Now, do you see that there's some repeats? Leucine's got about 6 codes here. Isoleucine has 3 here. Phenylalanine has 2. There's several repeats because there's 64 words and only 20 amino acids. I call that a backup system. But do you see anything unusual up there that's not one of those abbreviations? It's written in a little different color. TERM. Can you read that from the back? TERM. That means Terminator. And those 3 codes all tell the system that's working using this language, stop reading. There's another code built in there that says, start reading. Eyes up here. A protein is a string of amino acids. Here it is. Amino acid 1, amino acid 2, amino acid 3, amino acid 4, amino acid 5, amino acid 6. The amino acid has to start somewhere, and it has to stop somewhere. So in this language, there's a code that says to the DNA, start reading, read, stop reading, and between those two is a string of amino acids which makes a, excellent, only it was terrible, say it louder. A string of amino acids is a, exactly. And this language tells your body how to build that string of amino acids. I think you got it. So let's proceed. Here's what has to happen in order to make that building take place. You have to have transcription, migration, and translation. In just a moment, I'm going to show you a video that's much more fun than what I'm about to do. But you got to get this first. You got to transcribe the information off of the DNA up here in the nucleus. This is where all the information is. You got to get that copied. That's called transcribing. And then you make messenger RNA, you mature it, and then you migrate outside the nucleus out here to the ribosomes, and it is translated into building a protein. That's what happens. I'm going to add one thing to that right here. Every step of that process requires, let me say it again. Every step of that process requires, and lots of them. So you better eat your protein, that's right. Folks, it takes proteins to make proteins. You won't build a single protein in your body if you don't have proteins to help build it. So one of the grand questions I would like to ask an atheist is, how did this ever get started? It works like an amazing machine. You got to have both DNA, RNA, and proteins working in a finely tuned process that is, as we said last night, just right, or you don't have proteins. Neither do you have DNA. So how'd that get started? It's a serious problem. So let's blow this up a little bit. Here's the DNA. And it has to unzip, it has to copy, and then it has to be matured, and your messenger RNA has to migrate outside the cell. This takes a whole bunch of proteins. This takes proteins. Getting outside the nuclear wall takes proteins. Everything about that takes proteins. The ribosomal RNA is also made from the DNA, and there's a whole story about that. I'm not even talking to you about that tonight. The transfer RNA is also coded in the DNA, and that's another whole story, and I'm not talking to you about that either. But is that going on at the same time? Yes. Now let's go to the next one. Here is the messenger RNA coming out of the nucleus, and it's being picked up by the ribosomes. Would you say that looks like two ducks hugging each other? That's just a picture, class. But they do close in on the messenger RNA, and they read it like a tape through a tape player. You kids do know what a tape player is, don't you? Okay. And then based on that code, this process builds a protein which comes out the bottom here that's made up of methionine, glycine, isoleucine, valine, glucine, cysteine, and so on. Because a string of amino acids is a? Exactly right. So you've just learned the process. Now, class, what I want to show you next is one of these Drew videos that makes it come alive. I told you about this guy last night. He's an amazing animator. So we're now going to look at a video clip that animates how this happens. And I'm going to be the moderator. Michael, do I go forward? There. Let's get over here. All right, excellent. Stop right there. This is the start of a gene for a bone strength protein. You're getting ready to build a protein class. Here's the DNA strand, and here's a glob of, let me count with you. Every color is a different protein. There's protein number 1, there's 2, 3, 4, so far. Those proteins have to glob around the DNA, and there's a process they have to go through to allow the DNA to be copied. Proceed, Mike. So here goes. Here comes a vitamin D. Stop right there. You see the vitamin D attacks this guy and turns him green. No, he doesn't turn him green, but that's what they do. Because he activates him. And that now activates this whole complex to tell it, time to make a gene. Time to make a protein code. All right, proceed. So there he is. And here comes another glob of, what do you think? Protein. Stop right there, Mike. Here's another glob of protein along with a special protein down inside there, the dark blue. That's called RNA polymerase. A little piece of news for you on a pop quiz. If the word ends in ASE, it's an enzyme, which is another protein. Okay? So you got another glob of proteins up here, and there's that enzyme RNA polymerase. Now watch what happens as the vitamin D activates. Go. Stop right there. He sets loose the RNA polymerase to start writing down the RNA, and as it does, it's unzipping the DNA, making RNA copies, and continuing to zip. Little sidelight here. Have you ever had trouble zipping something up? Yes. Thank you. There's an honest person. So does DNA. It's all convoluted in there. You unzip it. It's not easy to zip it back up. Did you know there's a special just to help it zip back together? That's thrown in free of charge. That isn't on the screen here. All right, here we go. We've got the RNA polymerase writing along the DNA and copying it so that you get the RNA. Now go ahead. I love this. Here he rides, and the DNA is going this way. The RNA is being copied and going this way. And you're making a transcription of all the information on that DNA, and you're making an exact copy on the RNA. Is that amazing? Stop. Now we've blown up the RNA polymerase. That's this glob here. And can you see all these little pieces? How do you make a copy of something? You got to bring in all the information that makes the pieces. So they're constantly streaming into that RNA polymerase and building this RNA as the DNA passes through. The transcription, ladies and gentlemen, can I get it across to you? This is complex. All right, move on. Now here you get another picture. Stop right there. Now you're down inside and you're looking at the unzipped DNA. Mike, you need to go a little farther because there's some names that come up. Right there, stop. Here is the DNA unzipped. Here is its code. You see G, G, T, A, A, G, and so forth, the 3-letter codes along the band here of the DNA, and the copies are coming along and matching those pieces one by one as you go through this process, and then the RNA is being released, making a big, long strand with that information on it. Now, the problem that I've always had to be able to illustrate this is they're doing it so slowly. This guy fixes that. You watch. Go. Now, that looks pretty fast, but that ain't nothing. Because here's the way it really is. Stop. Folks, that's what's happening inside your cell every second you're sitting there. Because your body's building proteins at a rate of thousands per second in every cell of your body. No wonder you get tired just sitting there. Go. Look at this. Incredible. This is happening at an enormous rate. Now you're back to the other screen. Stop just a minute. The transcription is taking place, but you saw what all's going on down inside there. As the RNA is being constructed in the gene transcription process. That's step one, class. Okay, go. When it is finished, hold up, stop. Can you back up just a little bit? How did that transcription process know when to stop? Because there's a code that says stop. When you're reading it that fast, you come to the code that says terminate. It stops reading and lets the RNA go. Go ahead. Well, that was fast. Can you go back again? There we go. So what happens is you're reading and you're reading and reading along, and you come along to a thing that says terminate, and then go ahead. You stop and you let him go. Whoa, stop. See, they just left out of this video that he's way back up here with the DNA, and he has to migrate across there and go out one of these holes. And they also don't show you that when that RNA comes up to the holes, do you think that hole's going to let just anybody go through there? No. What keeps it from going through? What do you think? Exactly right. There's a protein that looks like this. When that RNA comes up there, it opens up and says, won't you come on through? And when he gets through, it closes back down. And on the other side of that hole, there's another to guard that side. You can't just let anything in and out of the nucleus. Are you kidding? There are proteins guarding the gates. All right, let's go on. So now the RNA is outside in the cytoplasm of the cell, and it's now going to be picked up by the ribosome. Boom, stop. Next week, we're doing 3 days on the ribosomes. No, we're not, but we should. That's another whole story, folks. They come and sit down on there, and then they take this messenger RNA through it and read it. You see all the messages on here? 3-letter words. Go. So here they go. They're going through, and inside, now you see the bigger picture. Stop right there a minute, Mike. Here's the ribosome, here's the messenger RNA, and here's the little guys bringing up the information. We'll talk about them in a minute. Go. All right, here's a blow up those little guys. Their names are transfer RNAs. And they're bringing up the amino acids up there so you can build. Stop right there. No, go on just a little further. A little farther. Keep going. Right there. All right, here's the transfer RNA, and it's carrying the amino acid into the ribosome so you can copy it. This transfer RNA is specific for that amino acid. Class, can you remember how many amino acids there are? 20. There is precisely 20 transfer RNAs, each one for the specific amino acid that it's designed for. You notice how I use that word? Designed for. Each transfer RNA is for a specific amino acid. Now, Mike, I'm going to test your stop and go abilities. Your job, class, is to watch the tail end of this thing because you're going to have pictures of the different amino acids showing up. Go. Stop. Go ahead. There. Go ahead. There. Go ahead. There. Go ahead. There. Go ahead. Have you had enough of this? That is showing you a lineup of the 20 different transfer RNAs with a specific amino acid stuck to the end of it. Now, do you think they look like that? No, class, that's a picture. But that's what's going on. All right, let's go, Mike. Back to the action. We're reading off the message inside this ribosome, and now you got a picture of what's going on inside. Stop right there. Here's the transfer RNA. It's reading the code off of here and exactly matching it, and up here is the amino acid that's being added to the chain of the protein that's being built out this end. Notice, isn't this interesting? The code is down here by the messenger RNA and the transfer RNA, and the protein's being built up here at a distance across the transfer RNA. Incredible. Folks, there isn't a human being that could have designed this as magnificent as it works. Let's keep going. All right, so you can see that's going pretty fast, but it's not near fast enough. So here we go. Now, you're trying to give you an idea of how fast. You see how many RNAs or transfer RNAs are going in there? Reading and zapping and zapping and zapping and zapping. Faster! And up here, the protein's being built. See it? In this case, it's hemoglobin in your blood. And by the way, it is red. I'm in awe, class. Now, what you don't know is there are 16 other things going on at the same time that we told you nothing about. And out comes a protein constructed of the precise amino acid strings wrapped up in a three-dimensional shape that is precisely that it needs for that particular protein. And if the shape does not turn out right, it doesn't work. And this, class, takes place thousands of times per second in every cell in your body, every second that you live. Isn't it interesting what Mother Nature did? I say I could stop my lecture right here. And if you were ladies and gentlemen of a jury, I would say to you, ladies and gentlemen of the jury, if you can believe that this system with a language in it that we know how to decode and read that uses the language at a rate of thousands per second to build stuff without mistakes, you can believe that happened by natural causes, by natural small changes over millions of years acted upon by natural selection. I have a bridge I want to sell you. That doesn't exist. But there's so much more than I've told you about. We have learned so much more about the chemistry of living things in the last 50 years. All of this was known by the 1980s. What we've learned since is beyond imagination. Because you see, class, the living cell is really a self-replicating nanoscale robot. Why do I say that? It's self-replicating because it can and does reproduce itself. We showed you that last night. It's nanoscale because the cells are quite small and can manipulate single molecules. It's a robot because its activities are carried out unconsciously and automatically by precision molecular machines that follow ordinary physical laws. And we've learned how to figure it out. And people say, wasn't I amazing for figuring that out? Instead of, isn't it amazing what God did? All right. I didn't warn you tonight. I don't allow sleeping. Some of you are sleeping. So what I want you to do, because I have just a few minutes left, we're all going to stand up and you're going to wiggle. Stand up. Because if I were you, I'd be asleep too. This is heavy stuff. Well, you can turn it off. I've been teaching chemistry too, you know. But I don't want you to miss this next piece. So, okay, shake yourself a little bit. Nobody's allowed to leave. Now, sit down and let's go. Molecular machines. Tonight I want to delve with you into one more molecular machine that's just utterly astounding. I already introduced you to these last night, so we're not going to tell that story again. I want to ask you at least, do you know you've got cilia all in your body? You know what cilia are? Little hairs. They're everywhere. Some of them you don't want, but some of them you really need. Every mucous membrane in your body's got cilia around it. Let me tell you one really important one. Do you see here in your lungs? Right here at the primary bronchus, that's covered with cilia right there. Here's a picture of them. Those cilia help you get rid of stuff that doesn't belong in there. And they're flopping around like this. Cilia usually wave like this. And did you know there's chemistry to that motion? I can tell you how that works, how a cilia waves by chemistry. Did you know, class, that there's a chemical process for building cilia that we could spend the next 6 weeks on? And did you know it involves kinesin walkers and dynein walkers? Kinesin walkers walk out this way as you build the cilia. Dynein walkers walk back this way. And there's a whole process built in there that we've learned all about. It's an incredible story. I wish I had time to tell you. But that's not my subject tonight. Cilia, all they do is wave. But that's a phenomenally complex thing, and if you didn't have them, you're dead. So quit smoking. But I want to talk about the bacterial flagellum. You say, what's that? Well, I want to introduce you to the bacterial flagellum. First of all, you know that a bacteria is a single-celled organism. Did you know that your intestines is full of them? I was reading today, your intestine has more variety of species of that kind of little beasties than anything else that we know of. It's full of them. So here we go. Michael, you're my man. This is a picture under an optical microscope of some little bacteria swimming around in somebody's intestine. So just imagine you got these guys swimming on there right now. Okay, here we go. Here's one type. It's got one cilia, and they move around pretty well. And I could talk to you about those, but I'd rather talk about the next class that's coming up here next. Oh, there it is. Look at them move. Keep going, Mike. Let them see a little bit. Whoop, 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 stop. Those are E. coli. You ever heard of that? There are some E. coli species that can make you very sick. But there are a whole bunch of them that are just perfectly fine, and they're part of your biome, and if you didn't have them, you're in trouble. So you got these little beasties floating around, and you're swimming around all the time. And how do they swim, class? They swim with a flagellum. And a flagellum is just not a normal cilia that just waves. A flagellum rotates. And in that little bacteria, there is a machine that makes it rotate. And let me take just a minute and share you a few statistics. I'm a math guy. It's all numbers. A single-celled E. coli has 4 to 10 flagella. You know why he can go so fast? He can have 4 flagella all wrapped around each other. Woo, 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 woo. Up to 10. Howard Berg, a Harvard biophysicist, called the flagellum the most efficient machine in the universe. It does what I'm about to tell you in microseconds with almost no energy. If we could figure out how to do something like that, we'd never have energy problems again. The motor rotates anywhere from 6,000 to 17,000 revolutions per minute. That's 283 per second. And the filament that it drives can go up to 1,000 RPMs, which is 17 per second. That's this thing doing this. I can't even do it 17 times in a second. But here's the amazing thing, class. Not only does it do 17 times in a second, but in a quarter of a second, it can turn the other direction. It was going clockwise, and it can go counterclockwise in a quarter of a second. And you know what activates that? Light hits the surface on a light-sensitive spot on that bacteria and sends a chemical system that is a cascade of chemical reactions that I wish I could explain to you. It's incredible, and it turns that motor switch from this way to that way. I have a whole lecture on eyes. The light-sensitive spot for a bacteria is extremely complicated. Don't tell me that's the first step toward the evolution of the human eye. You can't even get to that one and explain how the chemistry all got going. But the flagella is a motor like you've never seen. So here we go. Mike? Keep going. All right, stop right there. Here's a picture of the E. coli bacteria. Here is the flagella extruding from it. You notice this one has 4. This flagellum right here is about 10 to 20 times as long as the bacteria itself. And the amazing thing is, not only does he have it, but he builds it. So how did this evolve, class? I mean, what you do is you've got to evolve not only the machine that's probably the most exquisite and most efficient machine in the universe, but you've got to build the machine too, from nothing, from what's ever in that cell, without a straw boss. All right, let's go ahead. So we're closing in now on this flagellum, which you can see enters into the cell wall of that little bacteria right there, you see? Here's the filament, and here's the hook, extremely important. And down inside, you have the basal body. You notice how it went through 3 layers of that lipid bilayer, and here's the basal body of the machine that's made up of a whole bunch of complex parts. There's a rod, there's a bunch of rings, and they're connected through the cell membrane. And it rotates. That's up to 17,000 times per minute. Stop right there. Look. Everybody's eyes up here. If something's rotating 17,000 times per minute, do you think it might move this way and that? Yeah. You better have something to stabilize it, don't you think? That's what the stator does. The stator is hooked to the peptoglycan layer, and it's stuck there, and it keeps that thing rigid so that it can rotate and spin that filament so that thing can swim. Go ahead. There's the stator, and here's the rotor. Every one of those parts is critically important, and they work like a charm. It's incredible. Now, stop right there. What I want to tell you next, if you don't remember anything else from tonight, I want you to remember this. I have done a miserable job of explaining that machine. It's the most amazing, complex machine you've ever seen. But the amazing thing is, when this little bacteria divides and makes 2, it does not copy the flagellum. Are you with me? So how does it get the flagellum? It has to build it from the bottom up and start over. And it does it based on the code in the DNA and all those heavy working proteins. Not only do you have to rebuild the protein, you have to build the proteins to do it, but those proteins have to build the whole machine. So this video I'm showing you was produced by the Japan Science and Technology Corporation, so you could be envisioning what's been discovered in the last 10 years about how bacteria rebuild flagella. You say, why are these people spending so much time on a one-celled organism? Because they can kill you. You better learn how they work. And by the way, you got a bunch of flagella inside of you too. Did you know that? I'm not at liberty tonight to talk about some of them, but you can probably imagine some things you have swim in waters, and they have flagella. And it's very important they work right. So thank you, Japan Science and Technology Groups, for showing us this. Because here's what we've learned. This thing is built from the bottom up, piece by piece. Every time that bacteria divides, it has to build this flagellum again. It takes 20 minutes. So if you got 10 of them, you got 20 minutes for each one of them. So here we go, Mike. You're going to watch the building of a flagellum. It starts with 26 copies of the Fly-F protein that are just done like that. Makes the MS ring. Below that, the Fly-G protein makes its piece. And below that, the Fly-M and the Fly-N proteins, do you notice these are all different proteins? Make their part. Then we come to the rod, which has to be constructed from the inside, and it makes that rod grow right up in between with these proteins that are on top. Those guys have to drill through 2 layers of the cell in order to get outside. So the rod proteins and the rod cap do the job as you continue to build, and then as you've broken through, you form these little rings that are bushings that stabilize it as well, and then you dismiss the hook cap or the other cap, stop right there, and you build a hook cap that's designed to build this hook, which is the stable force that holds that filament, which is going to flop around. I have to tell you this little fact. That hook that you see there has to be exactly 55 nanometers long. If it's longer than that, it doesn't work. If it's shorter than that, it doesn't work. So the little bacteria, when he rebuilds this hook, has a method by which it is precisely 55 nanometers long. This little hook cap does the job. It's got a counter built into it and a timer. Keep going now. And it builds till it gets exactly 55 nanometers long, and it stops, is released, and then you have the filament junction proteins necessary, and then you build the last little cap made out of 5 distinct proteins, and we call her Twinkle Toes. Stop. What you see here, class, is a protein coming out for each of these strands. It comes out folded. She helps it unfold and takes its specific place in a circular order around this filament. And now watch what happens. Why we call her Twinkle Toes. Go. Faster. Stop right there. You see this beautifully formed filament? Every piece of it is orchestrated by Twinkle Toes. And the reason she does that, she got 5 feet, and she rotates around. There's 5.5 spaces, so she rotates. There's a half space left open. That's where that protein goes. She rotates. The next protein goes to the next space. She rotates. The next protein goes to the next one. That's why it's in perfect order. And class, anybody want to take a guess how many times Twinkle Toes rotates before she's finished with that filament? You boys want to guess tonight? They were way off last night, some of them. It can be 30,000 times that she's rotated to add another piece of that filament and build it. And guess how fast? Well, you know. Let's finish. And that happens, class, every time one of those guys divides inside of your intestine. They call it your gut biome. And you wouldn't be alive without it. Because the process is, you want to say it with me? Just right. Next slide. I guess I can do it. Every one of these are multiple protein processes. Each protein is complex and suited for its function. Each machine is highly sophisticated, intricate, dynamic, and elegant. These machines are spontaneously self-assembled in the cell. And there are thousands of them in every living cell. That's why I say with you, class, it is more reasonable than ever to say we have a great and grand designer. This did not happen by natural causes. And anybody that thinks so needs his head examined. And that's my lesson for tonight.